Okay, in this video I'm going to talk about the Miquel's theorem. So the theorem can be stated as follows. So we have a triangle. We have a triangle ABC, and we choose 3 points on the sides of this triangle, like arbitrarily. So we choose, like, here let's denote it by C prime, here let's denote it by A prime, and here let's denote it something here by B prime. So arbitrarily choose 3 points on each side of the triangles, and then we draw the circumcircles of the 3 triangles. So basically of this triangle, we draw the circumcircle of this triangle and of this triangle. So we draw the circumcircles of each of these triangles. So let's draw them something like this, and like this. And the theorem states that these 3 circles intersect in the same point. So like here it's not, they don't intersect, but actually they do. So it should be something like this. So they intersect in the same point. They'll pass through the same point. So let's write it. So the theorem says that the circumcircles of the triangle A C prime B prime, triangle B A prime C prime, and the triangle C B prime A prime intersect in a single point. Yeah, so let's consider the proof. So I will draw another picture. So again we have a triangle, we have two circles here. So A, B, C, this is B prime, this is C prime, and this is this is A prime, and this is C prime. So basically what we are going to do is, so first we draw only 2 circles. So the circumcircles of the triangle A C prime B prime and C B prime A prime. So the 2 circles that are now shown in the picture. So, and now what we are going to do, so we consider the intersection point of these 2 circles as let's say P. So this is the point P. Or let's write it closer. This is P. And so what we are going to prove now is that P belongs to the third circumcircle. So if we prove, so let's write, it is enough to prove. So it is enough to prove that the points okay, let's write it fully. So that P belongs to the circumcircle of the triangle B A prime C prime, right? So if we prove that, so if P lies on this circle, then it follows that all three circles intersect in the same point, which is the point P. So, but to this, it is enough to prove. So this would follow from the fact that, like the 4 points. So this would follow from the fact that the points B, A, P, C prime lie on a single circle. So we are kind of restoring the proof from the end. So like what we need to prove, and we are moving from the end of the proof. So this is it. So then it is enough to prove this, and further this can be restated as the fact that so here we have points like comma separated. The points B, A, P, C prime lie on a single circle, and another way to put it is that the quadrilateral B, A, P, C prime is cyclic, right? This is the same thing. So if you prove that this is a cyclic quadrilateral, then the statement of the Miquel's theorem would follow. Okay, so it is enough to prove that. So now we consider these segments. And we notice that the quadrilaterals A, B prime, P, C prime, and the quadrilateral C, B prime, P, A, they are cyclic, right? So this quadrilateral and this quadrilateral, right? They're cyclic because like we directly like by construction, because the P is the intersection point of the two circles, so there each of these quadrilateral is inscribed in the corresponding circle. So they are cyclic, and therefore we can express their angles. So one of the criteria of the cyclic quadrilateral, so let's remind that separately. So if we have a quadrilateral then it is cyclic if and only if these two angles are equal. So if an angle at one vertex is equal to the external angle at the opposite vertex. So that is the, if you write this is A, B, C, D, so A, B, C, D is cyclic if and only if the angle D is equal to the external angle B. Yeah, so this is the criteria of a cyclic quadrilateral, and we are going to use it here. So here, if I remove slightly the okay, so basically we apply it to this quadrilateral, and we write this angle is equal to this external angle, right? So they're equal, therefore, so I will remove now this. So therefore the angle AB prime P is equal to the angle B C prime P, right? So this angle is equal to this angle, and similarly for the second cyclic quadrilateral we have that this angle is equal to this angle, right? Also we have that the angle C B prime C B prime P is equal to the angle B A P. So this angle is equal to this angle. And from this we conclude that, yeah, so now we considering these two equalities, so on the left hand side in these two equalities are the angles that are like when we add them to each other, A B prime P and C B prime P. So this and this, like their sum is 180 degrees because it's the full angle AB prime C. So when we sum these two equalities together, what we get is that the angle, so we have, let's write it here, the angle A B prime P plus the angle C B prime P is equal to angle B C prime P plus the angle B A P, right? Just the sum of these two equalities. Now on the left hand side here, this is equal to 180 degrees. Because it's the full angle. It's this A B prime P plus C B prime P. So it's the full angle. 180 degrees. And on the right hand side, so what is on the right hand side? On the right hand side is these two angles BC prime P, this angle, plus BAP, this angle. So these are two opposite angles in the quadrilateral BAPC prime. So these are two opposite angles in the quadrilateral BAC BAPC prime. Okay, BAPC prime. So on this picture it's this quadrilateral, right? So the P is, okay, the P is here. Yeah, so the quadrilateral that I highlighted, this sum of two angles are the sum of two opposite angles in this highlighted quadrilateral. And we just proved that it is 180 degrees. But like another criterion of a cyclic quadrilateral is that the sum of the two opposite degrees or opposite angles in this quadrilateral is 180 degrees. So from this fact, we conclude immediately that BAPC prime is cyclic. And we recall that this is exactly what we needed to prove. BAPC prime is cyclic. If we prove that, then like we previously established, that this is enough to prove the theorem. So this is exactly what we just proved. So this concludes the proof of the Miquel's theorem.